When a fire breaks out, the difference between a minor incident and a total disaster comes down to a matter of seconds. You grab an extinguisher, pull the pin, and rely entirely on the immediate, powerful burst of suppression agent to do its job. Our confidence in that split-second moment usually relies on a simple visual indicator. We look at the small dial near the handle and check that the needle is resting in the green zone. For standard dry chemical powder extinguishers, that gauge accurately reports the tank's readiness. The physics are linear. As the powder depletes or the canister leaks, the internal pressure drops. The dial reflects exactly what remains in the tank. But carbon dioxide extinguishers are different. If you examine the valve assembly, you will find a smooth piece of metal where the gauge should be. There is no dial, no needle, and no green zone. In an emergency, this absence leaves the user with a significant unknown. Without that needle, there is no quick way to see if the heavy cylinder is fully charged or if the gas leaked out months ago. Engineers leave this gauge off because the thermodynamics of carbon dioxide make a pressure reading almost entirely meaningless for determining how much gas is left. To understand the missing gauge, we have to look at how CO₂ is stored. Packing enough of it into a portable extinguisher requires extreme compression. Under this pressure, the carbon dioxide exists in two states at once. A portion of the gas settles as a liquid at the bottom of the cylinder, while the remaining space at the top is filled with pressurized gas. This creates a state called liquid-vapor equilibrium. The liquid at the bottom constantly boils off just enough molecules to maintain a specific, constant pressure in the gas section at the top. If you use the extinguisher, or if it develops a slow leak, the liquid level drops to replace the lost gas, immediately restoring the internal pressure to its previous level. Because of this equilibrium, a cylinder that is 90% full and a cylinder with only a few drops of liquid left will show identical pressure readings. If a manufacturer installed a gauge, the needle would stay in the full zone until the very last bit of liquid evaporated. The user would only see the pressure drop when the extinguisher was already essentially empty. There is a second variable that makes CO₂ pressure an unreliable metric: its extreme sensitivity to the temperature of the room. On this graph tracks internal pressure against external temperature. On a hot day, the CO₂ gas expands significantly. This causes a massive spike in pressure, even if the amount of gas in the tank remains the same. In freezing weather, the gas contracts, and the pressure can drop well below operational norms. The tank is still full, but the internal pressure suggests otherwise. Because the weather causes these constant fluctuations, a gauge would produce a stream of false alarms, indicating the tank is overpressurized in the heat and empty in the cold. If internal pressure is a thermodynamic dead end, safety inspectors need a different way to verify that an extinguisher is ready for use. The solution is found on the collar of the cylinder. Every CO₂ extinguisher has its tare weight, the weight of the empty metal canister, stamped into the metal at the factory. During a maintenance check, inspectors bypass the valves and dials entirely. They simply place the entire unit on a calibrated scale. Mass is unaffected by the gas's liquid vapor state or the outside temperature. By subtracting the stamped tare weight from the total weight on the scale, an inspector knows exactly how many kilograms of CO₂ are inside. A pressure gauge only monitors the behavior of the gas, which changes constantly. A scale measures the physical amount of the gas itself. When safety depends on equipment reliability, engineers have to look past mechanical indicators that can be fooled by the environment. In the case of CO₂, they rely on the most consistent metric available, the physical weight of the material.